Okay, today we're going to go over parametric second derivatives. That is the derivative of a curve represented by two separate equations, those being the x and y. So the equation for second derivative is a bit convoluted. It's a bit difficult to understand, I suppose, but not that hard to memorize. So I'm going to first start off by telling you the derivative of a parametric curve, and that is dy dx. This can also be expressed by dy dt over dx dt. This being the derivative of the y function, so the y equation, this being the derivative of the x equation. Now the second derivative, this over here, can be represented by the derivative of the entire function, or the entire derivative of the curve, over the denominator of the original derivative. So just keep that in mind. And yeah, let's get into the practice problem. Okay, this is practice problem 1, and I lied. It is in fact the only practice problem. So the question states the path of a particle can be expressed by x equals e to the power of t times natural log x, and y equals 5x cubed minus 1. Find the acceleration of the particle at t equals 2. Now, if anything, we should find the acceleration in a vector sort of sense, but we're not going to do that today. We're just going to find the second derivative. So we're going to begin by finding the first derivative, which is dy over dx, which, as you know, is dy dt over dx dt. Now, we don't know what either of these values are, or expressions are, so we're going to start off by finding dy dt, which is just the derivative of the y function. So dy dt is equal to 15x squared. So that's quite simple. Now dx dt, on the other hand, is a bit more complicated. I don't know why I made it so complicated, but nonetheless, let's get into it. We're going to have to employ the product rule. So 1d2, meaning the first term, if you will, times the derivative of the second, which is, this right here should be t, sorry, and this right here should be t, because they are not going to be expressed in terms of x, since this is parametric and x is one of the variables. Okay, sorry, ignore that. Okay, so 1d2 plus 2d1. And this right here is our, these are our two derivatives for our two different expressions. Now, dy dt, also known as dx dy dx, also known as dy over dt over dx over dt, is the derivative of the entire curve. And we can just throw in our values or our expressions. So dy dx is equal to 15t squared over e to the power of t over t plus natural log x e to the power of t. However, we have to find the second derivative. So we're going to start out by just stating or equating the second derivative to something. And that is just the general form for it. So the second derivative is equal to the derivative of dy dx over the initial derivative of x. Let's begin by finding the derivative of dy dx. We can employ the quotient rule, I believe. And so we're going to say that d over dt, which just means the derivative of 15t squared over e to the power of t over t plus natural log t e to the power of t is equal to, and try to remember the mnemonic of the quotient rule, low d high minus high d low. I suppose it's not a mnemonic at all, but whatever. So low d high, so 30t times the denominator times, so low d high minus high d low, and this is going to be a bit difficult. Let's first write out the first term. the numerator. Now we have to find the derivative of the denominator. I don't know why I made this question so complex. So now we have to use the quotient rule on this as well. So that's simply e to the power of t minus t times e to the power of t over t squared. Plus the derivative of natural log t times e to the power of t, which is e to the power of t over t plus natural log t e to the power of t. And that is, well, not quite. We're actually not yet done with the derivative of the y derivative. We have to say that we have to multiply this by the inverse of the denominator squared. So e to the power of t over t plus natural log t e to the power of t squared. And this is finally, I believe, our derivative for our y derivative, or our y function derivative. And rather than just write this whole thing again, I'm just going to erase this and say that this is equal to our second derivative, even though so far it is not, because we have to multiply this by the inverse of our dx dt. So that our dx dt is this function right here, e to the power of t over t plus natural log t times e to the power of t. Just remember that from earlier. And so rather than, well, I suppose we could rewrite this as e to the power of t over t plus natural log t e to the power of t. However, we can simplify this further by just saying that, by just cubing this denominator here, it's the same thing. And so that is our final answer. That is the, oh god, at t equals 2. Okay. So apparently we're not yet done because I've just reread the question. So if you were to find the acceleration of a particle at t equals 2, as you could probably imagine, you just substitute t in with 2 for every instance of t. However, I don't feel like doing that, nor do I feel like using a calculator at this moment. So that's going to be the end of this video. If you have any suggestions for further videos, please put them in the comments below. Thank you.